Hi folks, I'm making this video here to kind of give an example of how to apply Newton's laws of motion for a rigid body moving in the plane. So in this example, what I want you to imagine here, we have this pickup truck, right? And the pickup truck is accelerating to the left at 6 meters per second squared. In the back of the pickup truck is this ladder. This here that you see in gray is a ladder. The ladder, the length I've written over here is 4 meters long. And it's sitting against this edge in the bed here, and it's supported by this frame that's built, right? So the actual forces on the ladder are applied here and here. And what you have to notice is that the truck is accelerating at 6 meters per second squared. Now keep in mind that that means the ladder's got to be accelerating as well. And the acceleration of the ladder will basically create clockwise moments about this point. So what we're going to look for here is the angular acceleration of the ladder. Now, it may or may not be, the ladder may or may not have an angular acceleration. It's conceivable that the ladder is just sitting here in equilibrium. Oh, I got to get an angle in here. The picture I'm using, that's a 60-degree angle. It's conceivable that the ladder is just sitting in equilibrium. So what we're going to do here is we're going to do a force analysis of the ladder, and I think what we'll do is start by trying to decide whether or not the ladder is actually going to be starting to rotate clockwise or not. So over on the left, I've already drawn the free body. I did that to kind of save video time here. So in gray here, there's my ladder, and I start analyzing the forces at it. The ladder has a center of gravity here that I labeled that point G. Put an mg vector at the center of gravity. All right, at this point right here, 2.5 meters up the ladder, a normal force is applied, and that normal would make a right angle to the ladder. I don't believe friction is going to be an important force here. Now, at this point, the ladder is kind of against the bed of the truck. The force exerted at the lower right end, it's definitely going to be kind of up and left. I don't see any reason to assume I see no reason to assume it's tangent to the ladder. So what I'm going to do is I'm going to call this point A and put reaction forces in the X and Y direction at that point. So the free body of the ladder looks something like this. Now, dynamics here, we need to draw the kinetic part of the diagram. Basically, the free body is a picture of Newton's second law. Net force in moments equals ma and I alpha. So on the right-hand side, right, I've got G here. I've put an max and may and an I alpha term for rotation. So there's the free body. Now, before we move on, I think what we'll do here is try to decide whether or not that ladder is for sure going to be accelerating. Now, in this picture, let's see, that is a 60-degree angle. And if we come over here, that makes this guy right there a 30-degree angle, I believe. Yeah. And what I'm going to do now is try to decide if this ladder is in fact accelerating. So the way to do that, I think, is this. We're going to calculate the acceleration needed to maintain equilibrium here. So as the ladder barely starts to accelerate, this normal force here would be going to 0. So what I'm going to do is I'm going to write an equation assuming this normal is 0 and assuming no angular acceleration, and therefore no vertical acceleration either. And what that'll tell me is it'll tell me the acceleration of the truck required so that the ladder just barely stays in equilibrium here. So what we're going to look for is we're going to set the normal to 0, solve for AX. So if we do, let's see, I can write a moment equation about A, sum of all moments about A, and I'm going to put a 0 here because I'm trying to find the acceleration here in the X direction that correlates to this just barely, this normal just coming to 0, but no real angular acceleration yet. So summing moments about A, we would have, let's see, the term mg times L over 2 cosine 60. The L over 2 cosine 60 is the moment arm for the mg. Keeping in mind the hypotenuse of this triangle would be L over 2. And let's see, on the right-hand side, right, we would have max times L over 2 sine 60. If, let's see, this thing's just barely starting to rotate, we have no angular acceleration and no a sub y here either, so I think we're done here. So I think what I'm going to do here is take a moment, pause this, and solve this for a and see what I get. Alright, so I'm back here, and after solving this, what I get is that I get an AX of about 5.7 meter per second squared. Now, here's what this means. If the acceleration of this truck were 5.7, we're less than 5.7 meter per second squared, like maybe 4 meter per second squared, this ladder would not start to rotate. We would have a normal force, the angular acceleration would be 0, the AY would be 0, and AX would equal whatever the acceleration of the truck is. When the acceleration of the truck hits 5.7 meter per second squared, pretty well exactly, this normal will be 0. Basically, the ladder's starting to come off, to rotate, come off this little pivot point here. The MAX would be the 5.7, still no real angular acceleration or a sub y. But this acceleration is, bigger than the 5.7. Not by much, but it's reasonably bigger. So now what's going to happen is this normal is in fact going to be gone. And we're going to have an AX, which is now unknown, an AY unknown, and an alpha. So now we're going to solve the problem knowing that the truck has a high enough acceleration that this ladder is going to start to rotate clockwise. So I'm going to stop this again here and get rid of work I don't need. Alright, so I'm back. So we're going to work the problem again now, knowing that this thing is starting to rotate, which means this force now is gone. And we'll start writing force equations. So one equation we can write is sum of all forces x direction equals ma in the x direction. Now I've got the acceleration pointing to the left, and I did that because even though this thing's going to start to rotate, overall from a frame of reference outside the truck here, this acceleration would be left. Center of gravity would still be accelerating left, just probably at a value less, not probably, will be at a value less than 6. AY will be some positive number because the center of gravity is going to start to move up. And alpha, I've got it shown clockwise. This will now be a positive number, assuming I write equations clockwise positive. So let's see. Acceleration, x direction, there's only one force there. Let's see, AX. And I don't see anything else, so that's going to equal ma in the x direction. Whoops, I see I got a little bit of a problem there in that I've got a force called ax and acceleration called ax. I'm going to go back here and call this capital AX and this capital AY. There. So capital AX is a force, little ax a acceleration. All right, now another equation we can write, sum of all forces y direction equals ma in the y direction. So looking here, that's with up positive. That's going to be ay minus mg equals ma sub y here. Okay. Another equation we can write a moment equation. We can either do that about G, or we can do it about A. I guess to eliminate, to not deal with these forces here, AX and AY, I'm going to go ahead and sum moments about point A. So sum moments about A, and I'm going to go ahead and do clockwise positive because that's the direction I've got the angular acceleration shown. Right? And the sum of the moments in this picture is going to equal the sum of the kinetic moments, right, about point A, and again with clockwise positive. So looking at this picture right here, summing moments about A, we're only going to have one of them. we're going to have mg times L over 2 cosine 60. Now, I've called clockwise positive, so that's going to be, that moment is counterclockwise about A. And that's it. That's the only moment about A. Keep in mind that the normal has, we believe is now 0. So summing moments about A is only going to have that one term on the left, right? Right-hand side. Now, keep in mind, we're summing moments about A. That's this point right there. And now we're going to have a lot of stuff happening. We've got this I alpha term, right? But we also have kinetic moments produced by the MAX and the MAY. So we're going to have, let's see, I'll do the MAX first, minus MAX times the distance we're going to need for that is this distance, that's L over 2 sine 60. Oops, and I ran out of room here. And the other kinetic moment term we have is for the MAY. Now that acts along this line, so the distance we need is L over 2 cosine 60. So the next line is going to be plus MAY times L over 2 cosine 60. All right, so we now have three equations here to analyze this problem. Equation 1, equation 2, equation 3. Now let's try to take a look at how many unknowns we have here. So AX unknown, AY unknown, alpha unknown, we're up to 3. However, over here, this AX, the force AX, also unknown, and the AY also unknown. All right, so we need to write some more equations here. 3 equations is not enough to solve this problem as it sits. So, it's important to take note. We've already written a force equation in the x direction. And we've written a force equation in the y direction, and nothing's happening in the z direction, so there's nothing more we can do about that. We've written a moment equation, and effectively that moment equation is in the k direction. This right here is actually about, in a standard XYZ, this we summed in the minus k direction, but still we've used that directional moment equation, and there are no moments in other directions. So we have exhausted the Newton's second law equations we can write for this system, at least independent equations. So we have to write some other type of equation. The other type of equation is going to come from the kinematic relationship between point G and point A. So I'm going to pause this for a moment, get rid of the stuff I don't need, and then we'll start writing kinematic type of equations. Alright, I'm back, gotten rid of a few things here. I stored these three equations, our three equations over here. So we had, I think, equation 1. I'm going to call this one equation 2. And third equation was too long for me to get in one line, but equation 3, hopefully I copied those down right. All right, so now we need a couple more equations. On the lower right here, I've done kind of a kinematic analysis here. Drew another picture of this ladder. Now keep in mind that here's G. We believe the acceleration has both x and y components. That's going to put acceleration G kind of up in the plane like this. So I went ahead and drew a vector for that. AGX would be AX, AGY is equal to AY. Now acceleration A, now that contact point is right here. So acceleration A has got to be exactly the same as the truck, 6 meters per second squared to the left. It does not have a y component to it. The only way this could have a y component is if we had significant rotation, but we don't at this point. When this thing starts rotating, the angular velocity is still 0. So there's no centripetal acceleration terms anywhere in sight yet. So now I'm going to go ahead and write an equation here that says this. Acceleration of G is equal to acceleration of A plus acceleration of G with respect to A. Right now, acceleration of G we can write, let's see, why don't we do AX in the minus I. I'm going to go ahead and use a standard XYZ coordinate system for this. Plus AY in the plus J. And that has to equal the acceleration of A, which we know to be 6 meters per second squared in the minus I, plus acceleration G with respect to A. Now, the acceleration G with respect to A, let me talk about that. I'm going to write this right here. there's two terms that can show up here, a tangential and a centripetal. So G with respect to A can be written, let's see, alpha cross position G with respect to A for the tangential acceleration. This one we're going to need. And then minus omega squared times the position vector A with respect to G, or position vector, let's see, GA. Right? Now, this term is for the tangential dynamics, the acceleration caused by the angular acceleration, and this we believe is there because we believe there's going to be an angular acceleration there. By the way, this is not divide. I just didn't have room to put this over here. All right, this would be, r omega squared is the centripetal acceleration of G with respect to A due to the rotational motion of the ladder. However, at the instant this thing starts rotating, it's not really rotating yet. All right, so at t equals 0, this term, the ladder, is not rotating yet, so we don't need this centripetal term here. All right, so all we're going to need is the alpha cross r G with respect to A. So I'm going to take a moment, pause this, and clean this equation up and try to make myself some more room. So clean it up a little bit, rewrote this equation up here, wrote the acceleration, the angular acceleration vector as alpha in the minus k, right, because I have alpha pointing clockwise. Position vector, G with respect to A, that's L over 2 cosine theta 60 to the left, that's the minus I, and then L over 2 sine 60 up. Now, this is a vector equation, so we should get two more equations out of this, two scalar equations, and we should be able to get this thing solved. So, I'm just going to keep doing right-hand side here. So, 6 in the minus I, put a little note consistent units here, that's 6 meters per second squared, plus. All right, so now, the next term is going to be alpha L over 2 cosine 60. Now, in the minus k cross minus I, let's see, minus k cross minus I got j out of that. And then the next term, let's see, we're going to have plus alpha L over 2 sine 60, and then the direction is going to be minus k cross j. So let's see, minus k cross j, I get in the I direction. I'm going to take a moment here and just double check these cross products. So let's see, minus k cross minus I get j again out of that, minus k cross j. I get I out of that. Okay, so that should be good. All right, so now, by comparing coefficients here, let's see. And I think what I'll do, all right, so we have ax in the minus I, 6 in the minus I. This here is a minus. I think what I'll do here is this. I'm just going to insert kind of a minus here and a minus here. So now I'm comparing things, everything in the minus I. So we can say that, all right, ax is going to equal 6 plus, oops, nope, minus alpha L over 2 sine 60, right? There is equation 4. And then equation 5 is coming from comparing y components, and we're going to have a y is equal to, let's see, looking to the right, alpha L over 2 cosine 60. And that's it. I don't see any more in the y direction, so let me double check that. Ay plus j is equal to this thing and the plus j. Poor j, but humor me, that's a j. So there is my equation, I think 5, so we should be good to go. I'm going to go ahead and pause this, clean it up, and see what we get. Alright folks, I'm back here. So this is just more algebra than I feel like putting on the page, but let me talk about where the solution is going to come from. Alright, so we have ay in terms of alpha right here. You can take that, you can sub it anywhere we see an AY. So looking over here at our three kinetic equations here from Newton's second law. So we can put that term here and here, right there in equation 2, right? Then anywhere we see an AX, we can put this. That can be subbed here into equation 1 and here into equation 2, right? That system of equations now, we won't have an AX or an AY, right? The unknowns will be alpha, AX, AY. It reduces down to a 3 by 3. Do some substitution on it, and what you get is what I end up with is 0.11 rad per second squared. I'm going to leave that as an exercise to the reader, and I hope this video helps illustrate how to draw free bodies for rigid bodies with motion in the plane, write Newton's second law equations, and then use kinematic equations to relate accelerations. So, hope it helps. Everybody have a great day.